renormalization, so-called renormalization. I don't know whether that's a good name, but it's a name that has stuck. Was finally how to do it technically correctly. It took a long time. So today we want to address something similar on the lattice. So in the lattice, so what is the continuum problem? Field theories are divergent because of our extrapolation of the action to arbitrarily short distances where we have had no experimental confirmation that those actions are really good. So you put in something and you pay a price for that. And the price is that almost everything you calculate is divergent. Okay? Now there are better ways of formulating this. Wilson, Schwinger, even Feynman has recognized that this is not a fundamental problem. At one point Dirac and others thought that this is such a serious problem that it might entail a completely radical revision of our ideas of space and time, and nothing so dramatic happens. Reason is essentially this: you have assumed physics to be valid in scales where nobody has tested anything, and so that knowledge, which is not really knowledge, assumed knowledge, has to be taken out. And the way it is taken out is done through renormalization. Okay. So anyway, however you want to understand it, you have to do that. So in continuum theories, you first regularize the theory. That means you introduce some cutoffs, could be momentum cutoff, or it could be dimensional regularization, proper time, whatever way. There are any number of regularizations that you can choose, and it is not even necessary that the regularizations have to respect any invariance. You can take a regularization that breaks Lorentz invariance, rotational invariance, everything. As long as the theory is regulated, it's fine. And of course, the price you pay for using a non-invariant regularization is that you have to add some terms to ensure the so-called ward identities of the theory are respected. If you do that, then everything is fine. So, regularization that way can be extremely of wide choice. So you regularize it, and all the Green's functions that you calculate now are finite. That's what the regularization achieves for you. But there is a regularization dependence, and the cutoff is physically arbitrary, and you have to remove it. So one point, anyway, maybe I shouldn't say it verbatim, I will go through the slides and make them at the right point. So let's consider this topic today, and that is the continuum limit of lattice gauge theories. We have already mentioned that the lattice in lattice regularization is not fundamental. At least we don't know at the moment whether there is a fundamental lattice, fundamental length scale, and so on. We have just introduced it as a regularization. The inverse of the lattice spacing acts as an ultraviolet cutoff for the theory. This is unlike condensed matter, where there is a physically dictated lattice, physically dictated lattice spacing, and there it is not a choice of regularization, and you have to live with that. But here it is not so. Therefore, it must be eventually removed, which means the lattice spacing should be taken to 0, which is equivalent of removing the ultraviolet cutoff to infinity. Now you may say, why did you introduce this lattice spacing and you are going to remove it? The same story in the continuum. We introduce a cutoff so that manipulations become meaningful, and then we remove the cutoff not of the original formulation but of a slightly modified version where you can remove the cutoff in a safe way. Otherwise, if you just put in the cutoff and immediately take it out, all the divergences are going to come back and you can't do anything about it. Same thing happens on the lattice also. Now hopefully in this limit, when the lattice spacing is taken to 0, all the memories of the lattice are removed. But this is non-trivial because even when, when the lattice spacing is taken to 0, the distance, for example, could become like what is called a taxi driver metric. Taxi driver, not in our cities, but maybe in cities of the West, where there is a grid-like formation of roads. He goes some distance in the X direction, some distance in the Y direction. His meter shows, a distance which is absolute, sum of absolute magnitudes of all the distances covered. Now this continuum, there is no lattice there, but that's not rotationally invariant. So hopefully when we remove the lattice spacing, we don't end up with a metric like that. In the language of the non-invariant regularization of continuum field theories, if you for some reason decide to work with a rotationally non-invariant cutoff, then when you remove the cutoff, the physics should become rotationally invariant. That's the analog of that, and this is not easy to guarantee. Likewise, Lorentz rotational invariances should all be restored. When you put it in a lattice, the group of rotations gets reduced to only the group of hypercubic rotations, and thus only a small part of the Lorentz rotational group. In the continuum limit, the full rotational group should be restored. And it turns out that not every lattice formulation will deliver that to you. There has to be something called a roughening transition. I'm not going to go into the details of that, but I'm just mentioning the names so that those of you who are interested can just follow it up. Now, how is the cutoff removed in the continuum? All the discussions of renormalization, now they have become very technical. They tell you about calculating wave function renormalization, this renormalization, that renormalization, various subtraction schemes, various regularizations. They are all very important technical details, but they somehow obscure the key message of renormalization. And if you try to follow that path literally in the lattice, there is no hope for it. You will get lost immediately. So first let's extract what exactly is the essence of renormalization, not the details, the essence of that. So we have some bare parameters in the theory, charges, masses, whatever they are, and let's collectively denote them by chi naught. And if you calculate, you end up with divergences. So you regularize the theory. Now calculations are finite modulo something called infrared divergences, and I won't get into that topic because that's very complicated. So for the moment we will assume there are no infrared divergences that are bothering us. then what happens? So you do all the calculations, they're finite, but they depend on this cutoff. Now at this stage of a regularized theory, whether the theory is renormalizable or not is not important. Even perturbative quantum gravity, which is known to be non-renormalizable, there is a perfectly well-behaved regularized version of that. So at this stage, they are only talking about regularization and not bothering about whether the theory is renormalizable or not. So now let's G be some observable mass, charge, scattering length, some S matrix which is observable of the theory. So you see, we can actually look at renormalization in a much broader context, not just of mass renormalization, charge renormalization, etc. So you calculate this observable in the regularized theory, and that will depend upon the Bayer parameters, cutoff, maybe momenta, etc., etc. Now at this stage, if you examine this G, for what happens when lambda is very, very large, you will find typically that this, for very large lambda, grows as lambda to some positive power b. So that if you try to remove the cutoff, namely take cutoff to infinity, these will again diverge. So you can't remove the cutoff at this stage. So what does one do? At this point, very broadly speaking, one introduces a dependence between the Bayer parameters chi naught and the cutoff lambda by fixing some physical quantity. Which physical quantity you fix should not really matter. So let's say it is some G bar. So this G bar x naught lambda is something which we'll call G physical for the moment. This induces a relationship between cutoff and the Bayer parameters. So we can call a new quantity which is renormalized chi such that chi r, chi naught lambda, inverting this relationship, gets fixed. Now you can, assuming that this works nicely, you can re-express the quantities G in terms of chi r and lambda. Now examine the behavior of this for large lambda. What happens, if you're lucky, is that this for very large lambda goes to some finite quantity plus some subdominant corrections where C is positive for very large lambda. So now lambda can be taken to infinity because this goes to 0 and this is insensitive to lambda. So this is how cutoffs are removed in the continuum theory. But one very important caution, that even after doing this G still depends on lambda. So after renormalization, you have not got rid of the cutoff independence. Everything is still cutoff dependent, but the dependence is very mild, is very soft, so that you can actually remove the cutoff in a safe and controlled way. This is important. Now we come to removing the cutoff in lattice theories. So if you view renormalization in this very, very broad way, then same thing can be done on the lattice also. In the lattice, the regularization is given by the lattice spacing, and the inverse of that gives an ultraviolet cutoff. But unfortunately, as we saw in the previous lectures, in all our partition functions, the lattice spacing has disappeared. You can't see it anywhere. So how do you banish something which you can't even see? That's a slightly technical problem for lattice. At least the way we have formulated it, where we scaled everything in suitable powers of lattice space. So you have to do something a little bit smarter. The strategy is very simple and most easily seen on the blackboard. So let's take some physical length scale, some Compton wavelength. Okay? Example. It's got some value. Now I have a lattice. I start off with a lattice where the lattice spacing is very large. When the lattice spacing is very large, you obviously can't ignore it, which means that the cutoff that you are using is very small. So you do better and reduce the lattice spacing no color chalks. Okay, no problem. So I take a lattice which is, let's say, much smaller but still larger than the Compton wavelength. That also won't do, and you keep on doing this till you have a very, very small lattice. So that this physical length scale to lattice spacing just becomes very large. So that is an alternative way of looking at the limit when the lattice spacing goes to 0. Now this ratio of a physical length scale to lattice spacing is nothing but one of the correlation lengths of the lattice theory. So this means the continuum limit of the lattice theory is equivalent to finding a regime where the lattice correlation lengths start diverging. Okay, they become infinite. Remember now our lattice is a classical statistical mechanical system. So we have to ensure that our classical statistical mechanical mapping of our original quantum field theory is such that it has diverging correlation lengths. This is highly non-trivial, and we will see what all it means. You can turn off the light. Before we go further, let's step back a little bit and get used to some terminology of classical statistical mechanics. The most important quantity of equilibrium classical statistical mechanics is the free energy. Because once you have the free energy, you can work out a lot of thermodynamic properties of the system. So the main aim would be to calculate free energies, and the free energy is related to the partition function, sorry, there should be a bracket closing there, e to the minus f of beta. Now it's quite clear that the partition function of the classical statistical mechanical system exists. Therefore, the free energy as a function of beta is a continuous function of beta is inverse temperature. beta is 1 over kT. So free energy is everywhere continuous, but that doesn't mean its derivatives are continuous. Okay? And that is where all the fun begins. First derivative discontinuous. Landau introduced this classification. First derivative discontinuous is called a first order phase transition. This is what happens in ice water, water steam, etc. But in this first order phase transitions, the correlation length may become very large, but it never diverges. So such phase transitions in our lattice CSM are no good. They will not enable you to take the continuum limit. They will reduce the cutoff dependence quite a lot, but never get rid of it. Now water steam also, first derivative is discontinuous. In the ice water, there is a latent heat of melting, and in the water steam, there is a latent heat of evaporation. And they are finite, because you know how much thermal energy has to be given to melt 1 gram of ice or completely vaporize 1 gram of water. However, if you plot the phase diagram, let's say water steam, it ends in a critical point. This end point of the water steam phase diagram is a phase transition with diverging correlation length. So that is the kind of phase transitions which we have to ensure in the lattice. Please turn off the light. Thank you. Now, the way the correlation length diverges, first of all, there is a critical temperature. The correlation length, as you approach the critical temperature, diverges, and it can diverge in many ways. Beta minus beta c to some minus delta, e to the minus alpha over beta minus beta c to some gamma, etc. These are called critical exponents. Yeah, enough. Now, the beauty is you can have a large number of statistical mechanical models which have phase transitions with diverging correlation lengths. The critical temperature may change for all these guys, but the critical exponents for a large class of them are exactly the same. And this is called universality. For example, if I take this critical endpoint of the water steam, its critical exponents are the same as the critical exponents of the three-dimensional Ising model. Three-dimensional Ising model has nothing to do with this water steam system, but still the critical exponents are the same. And this is called universality. This partly answers our question that we have ended up with so many different lattice models, different choice of lattices, different choice of discretization. The hope is that they all belong to the same universality class. So they may all differ, But when you take the continuum limit of these theories, they yield the same continuous field theory. Okay? Now, this is a bit of a folklore. It's generally believed to be correct, and there aren't any known examples, but there is no proof as such that this will always happen.
Proof of what? Proof of what does it mean?
Huh?
What is the statement? Proof of what?
What is that? Yeah. Oh, careful. Careful with your laptop.
You said proof doesn't exist. You said proof doesn't exist.
Yeah.
Proof of what does it
That you have this, everything will be governed by this universality class. That our entire lattice, family of lattice models now is all governed by one fixed point. It's more or less true, but it's not evident. Thank you. Fine. Now I belong to that family, or not should I say, that universality class of people who are only convinced by examples and not by proofs. So to me, they say one picture is worth 1,000 words. So to me, one example is worth 100 proofs. So I always try to construct examples which bring out the essence. Now, quite happily, I will give you now an exactly solvable example which will illustrate many of these ideas of the continuum limit of lattice gauge. It's a toy example. That doesn't matter. But the toy example has all the properties that we expect of more realistic field theories. And to see how it works in the toy example is actually quite illustrative. So what is the toy example? I don't know why my mouth is going so dry today. Sorry. This is our capital D equal to 1 lattice field theory that I introduced in the earlier lectures, which is actually quantum mechanics. Because when space-time dimensionality is 1 and you take away 1 for time and there is nothing left for space. It's quantum mechanics. But put to look like a quantum field theory in capital T equal to 1. That's okay. So this is my path integral. Everything is dimensionless. So lattice spacing doesn't appear anywhere. And now we will see how to remove the lattice spacing from this theory where the lattice spacing doesn't appear explicitly. Because that was the confusing part. Now, apart from this m square, there are really no parameters in this theory, and this looks like nearest neighbor spin models, but those nearest neighbor spin models usually enter the Hamiltonian, so the partition function has a beta in front of them. So we will arrange things so that this also looks like that. And what we will do now is, there should be actually 2 there. So I will introduce a beta. Instead of 2 there, I'll put beta. So for beta equal to 2, this becomes that. And now I will study this family, this statistical model, as a function of this inverse temperature beta. Why beta equal to 2 is so special, that will become obvious when we solve this model. Now, as I already told you, physics is contained in correlation functions. So correlation functions for this model are easily defined. It is just you introduce in the integrand phi 1 to phi n and divide it by the partition function. That's the thermal expectation value of this, product of fields. This is nothing but harmonic oscillator in disguise. So you can actually solve everything exactly. Okay? So I will do this. I will solve this. There are many ways of solving it. But I want to show you how to solve this by using the notion of a transfer matrix. Remember, we introduced the notion of transfer matrix as when we talked about when Euclidean Green's functions will reproduce the Minkowski-Green's functions, and the Osterwalder-Schroeder work said that for that there should be reflection positivity, and the reflection positivity also guarantees a positive transfer matrix, and that translates into the positive norm Hilbert space of the quantum field theory. So the transfer matrices in our context are very important, and in classical statistical mechanics, people like Baxter have used it to obtain miraculous results. They have solved large number of statistical mechanical problems exactly. Okay? So it's a very powerful technique, and I will show you how it works in this simple example. So what is a transfer matrix? So in this one-dimensional model, my lattice is just a set of points. So suppose I take, so let's say my time is going this way, phi n plus 1 here, phi n. So at each of these points, this can take a continuum of values. This can also take a continuum of values. The transfer matrix relates the configuration here to the configuration there. So it is labeled, switch off, hello. So it's labeled by the configuration at one time slice, quote unquote. There is Euclidean, so there is no time as such, to the configuration at another time slice. So it's an infinite dimensional matrix. And mathematicians would probably curse us for talking so glibly about infinite dimensional matrices, but that's our physicist's virtue, We are not afraid. Now in higher dimensions this becomes more complicated. For example, if I take 1 plus 1 dimension, then in this time slice you have to label all these values will go to label the transfer matrix. So it becomes more and more complicated as you go to higher dimensions. But that if you look up my notes, Nikef notes on lattice theory for non-specialists, I will explain how you can do even higher dimensions quite straightforward. In fact, we at one point set up transfer matrices for, pure gauge theories, and did a lot of very interesting investigations with that. So that's the transfer matrix for you. Now, our lattice can be one-dimensional lattice, can be just a line, but we will instead take it to be a very large circle of n points. Now, as n becomes large and large, this becomes a very large circle, and for all practical purposes, physics does not depend that you are actually on a circle and not in a real line. Sometimes you have to worry about this, but here it's fine to do that. Why do we do it like that? Because then the method becomes simpler. Otherwise, you have to worry about what happens at the endpoints and things like that. But none of the conclusions change, because this is really like a boundary condition at infinity. So then what happens? Let's look at our partition function here. It's integrated over all the field points at every point, and otherwise it involves a chain of transfer matrices. Yeah. So we will recognize that the partition function can be rewritten as transfer matrix taking 1 to 2, 2 to 3, come back to 1 actually. This should be n to 1. I'm sorry, there's a slight mistake there. And that is nothing but trace of the transfer matrix raised to the power n. So the partition function can be written in a nice and simple form in terms of the trace of a suitable power of the transfer matrix. And that's good, because now we know that this can be written in terms of the eigenvalues of the transfer matrix. We don't need any other details to evaluate the partition function other than the eigenvalues of the transfer matrix. Its eigenstates, etc., in the limit n going to infinity are not important. But they will become important at the next stage. So let lambda naught to lambda 1, etc., be the eigenvalues. This is an infinite dimensional matrix, so there will be infinity of these eigenvalues, and we will arrange them in decreasing order. You can formally prove that there is always a unique state with the largest eigenvalue for the transfer matrix. It's a little technical, and let's not get too deep into those details. Now, it's obvious that trace t to the n is simply sum of the eigenvalues raised to the power n, maybe with some weight factors which are the degeneracies of the eigenstates. Now, as n goes to infinity, clearly the largest eigenvalue dominates, and all the rest will become smaller and smaller. So, z beta can be written as the largest eigenvalue raised to the power n, and the ground state, I have taken it to be non-degenerate, but if there is some finite amount of degeneracy in the ground state, you can handle that. We will keep everything simple so that we understand what to do. Now, how do I determine lambda? You write down the eigenvalue equation, you expand it. All integrals are Gaussian because the transfer matrix is exponential of a quadratic. This is nothing but the harmonic oscillator quantum mechanics problem in disguise. And the harmonic oscillator, we can solve it exactly. When we were students, we were told that there are only two things you can solve exactly in quantum mechanics, and that is harmonic oscillators and the Coulomb interaction. Much later it turns out that the Coulomb problem can also be mapped into a harmonic oscillator problem with indefinite signature. So now, after so many years of struggling with physics, now we know that we only know how to solve harmonic oscillator problem. And you can easily work out the wave function or the eigenstate of the largest eigenvalue of the transform matrix is simply the ground state wave function of the harmonic oscillator, where alpha is, I have called m plus a squared as a somewhere. Let's see where that is. Yeah. Our 2 plus m squared, I have called it a. So the eigenfunction looks like that, where alpha is determined in terms of a and beta, and the largest eigenvalue takes this simple form. Straightforward calculation. Now let's investigate the first excited state of the transform matrix. In the case of the Hamiltonian, the ground state energy lies lowest, first excited state energy lies higher, etc., etc. In the case of the transform matrix, the largest eigenvalue is like the ground state, and the first excited state has an eigenvalue smaller, etc., etc. And this is because the transform matrix is like e to the minus the Hamiltonian. In fact, formally, you can write it like that and recover the Hamiltonian from the transform matrix. Again, this is trivially solved. Our first excited state must be orthogonal to the ground state. So there are many candidates. For example, this is again the first excited state of the harmonic oscillator, and you can show that the first eigenvalue is given by this formula, and with a little bit of algebra I can show that lambda 1 is indeed less than or equal to lambda naught. Now, as an exercise to you guys, I say find all the eigenstates, okay, harmonic oscillator. You can just do that. And since all the lambdas are positive, this shows the transform matrix is positive. This is what the Osterwalder-Schroeder condition, very formally for all class of Euclidean theories, ensured that if reflection positivity is there, then the transform matrix is positive. In this example, you can work out what reflection positivity is. I am not doing it, but you can look at Zeiler's notes. Very good. But so what? What we are interested in is a correlation function.
Excuse me, sir.
Can I have some light?
Excuse me, sir.
1 second. I want some light. Yeah. I'll come to you in a moment. Now we'll calculate the correlation, 2-point function. Phi n, phi of at 2 points which are some distance r away, and this is the thermal average, equals integral phi n phi n plus r e to the and then divided by the partition function. Okay. Yeah.
So you said that reflection positivity. Yeah.
So you said that reflection positivity ensures a positive transfer matrix.
Yeah.
So is the inverse true always? If I have a positive transfer matrix, is the reflection positivity always guaranteed?
Don't know. You know, it will be hard to work it out in the reverse direction. But it's a good question. You know, is reflection positivity necessary and sufficient for, you know, ensuring a positive transfer matrix? And I think the answer is yes. So if you have a positive transfer matrix, you know, then you cannot have a violation of reflection positivity. But I have not worked out the proof, so maybe you should. So there is a very nice trick to work out this correlation function. So let's take our circle and we start somewhere here and go to the next one through a transfer matrix, next one through a transfer matrix, etc. And suppose we start here with psi naught. Since if there is no other operator, then this is psi naught everywhere. In fact, if you start with psi I here, it is psi I everywhere, and therefore this 2-point function has the form, I'll mark 2 points here which are at, okay, first let's look at the partition function, and this says that it's simply a sum of lambda naught to the n plus lambda 1 to the n, etc. That's what we had earlier. And when n becomes very large, this is simply lambda naught to the n to a very good accuracy. Now I consider the 2-point function. So if I come here with ground state, at this point I have a operator and that makes it jump into the eigenstate psi 1, and it continues as psi 1 up to this point, and the operator here will make it jump back to the ground state, and so this will get a contribution which is lambda to the n minus r and lambda 1 to the power r, etc. If the more excited states, then you have to do this, you know, for all the excited states, and in between there will be some factors, which is psi naught, phi, psi 1, and it can depend upon n. So we call this some factor Cn. Then in the n going to infinity limit, the correlation function will be these factors Cn, lambda 1 over lambda naught to the power r. So the 2-point function can be worked out exactly, and this we can rewrite. Okay, I'm done. Switch it off. Yeah. So that is what I have here. And when R is very large, only this dominates. And when R is not so large, other excited states can contribute. But in this toy example, the only first excited state that contributes. We will rewrite this as e to the minus R over xi, where 1 over xi is minus log lambda 1 over lambda naught. And since lambda 1 is less than lambda naught, the correlation length is positive. So the 2-point function actually decays exponentially, and that is how, for example, masses are determined in lattice gauge theory. You just take the 2-point function in some channel and make the distance as large as possible, and from the exponent you can read off the mass in lattice units. So this xi here is the correlation length for this channel. And when lambda 1 is equal to lambda naught, the correlation length diverges. So if you can show for this toy model that lambda 1 can become equal to lambda naught for some beta, then you have a diverging correlation length for this extremely simple statistical mechanical problem, and you should be able to define the what is called the statistical continuum limit. It's a continuum limit based on the statistical mechanical theory of critical phenomena. Now, people from StatMech will tell you that in d equal to 1 with nearest neighbor interactions, you cannot have a phase transition. So here we have an explicit counterexample, and I'll let you think why this works. This is correct because it's just the only kind of mathematics that we can be confident of, namely Gaussian integrals, and nothing more has been invoked. And you should figure out why the StatMech folklore breaks down for this case. Now, how do you find the critical point beta c? And that is found by equating lambda 1 to lambda naught. Let's go back here. So when lambda 1 is equal to lambda naught, the critical point is given by beta c equal to a of beta c plus alpha at beta c. Which is this condition. So a, you remember, was 2 plus m squared, and m was in lattice units, so it actually is physical m multiplied by a. So in the leading order, you can ignore that term. But if you want to do this to higher orders, even that term has to be kept in. So the solution to this is critical beta is 2. And now we see why beta equal to 2 is very special. So at beta c equal to 2, the correlation function of this model diverges. Now let us find out how it diverges. In other words, what are the critical exponents for this model? Very elementary to show that the correlation function diverges as beta minus beta c to the minus a half. In the last lecture I said something incorrectly, that this toy model has the same critical behavior as QCD. QCD is essential singularity. That was another exactly solvable model that I had in mind. So this is what is called the mean field exponent. There is nothing mean about it. It's an exponent as good as any. The correlation length diverges in this case. So you can tune lattice spacing to 0. The lattice spacing, as beta approaches the value 2, keeps on shrinking, and exactly at the critical point, the lattice spacing has been tuned to 0. So this is how we get rid of the cutoff in lattice gauge. This is a very elementary model, but all the details are exactly the way it is supposed to be for more complicated matters like QCD or any theory that you study in the lattice. Now I'll give you a little exercise, because it's always a test of understanding whether you can work it out. When I was a graduate student, I had a very nice postdoc, also from India, and he told me, I'll give you one advice. Here you will hear a lot of people talking about beauty of physics, richness, and all that. Don't trust any of them. First, see if they can do a harmonic oscillator calculation. Okay, otherwise, all this talk of beauty. He was, of course, an extremist, but there's a point to it. You should be able to calculate. So I give you as an exercise for all of you to find out all the correlation lengths of this model. Do all of them diverge? Do they diverge at the same critical point? Are they independent or are they multiples of each other, etc. So, and then if you are still enthusiastic, there is a class of exactly solvable quantum mechanical problems, and see if you can cast them into equivalent classical statistical mechanical problems and investigate universality in that set of toy models, and you will get a lot of intuition about how all this works. So let's come back to the lattice, and as you can see, I'm getting tired and making spelling mistakes. When you're approaching 80, it's a little bit difficult to keep writing transparencies. So renormalization of the lattice amounts to exactly as in the continuum, keeping some physics constant. In this toy example, we kept the mass in that two-point function channel fixed. You could have taken some other correlation function and keep that mass fixed and see how things work out. So different choices of the physical quantities you keep fixed amount to different renormalization schemes. This is exactly as in the continuum. It may so happen that the classical statistical model is so complex that there are many sets of correlation functions and they all diverge differently, but within each set they're all at the critical point become proportional to each other. So in principle, a very complicated pattern of diverging correlation lengths are possible, and the continuum limit will be correspondingly complicated, or as some people say, it is much richer in physics. Okay, that's the only way we can get rich in physics. Now we can summarize all this by noticing that our mass, dimensionless mass, is physical mass in scale with respect to lattice, and inverse of m is the correlation length. So you can rewrite it as the lattice spacing as inverse of the correlation length, and as the correlation length diverges, A goes to 0. Depending on the critical exponents of the diverging correlation length, you will see how A approaches 0 at the critical point. Now one thing, if you have a set of correlation functions which are proportional to each other, so that they all diverge at the same point and in the same way, then the ratio of two physical masses is simply the ratio of the lattice masses, but this is expected only very close to the critical point. In the early days of lattice gauge theory, people would do strong coupling analysis because it's like high temperature expansion in statistical mechanics. You can sum, you can use Pade approximant and this, that, and they would compute masses, and some of them found that even though this is strong coupling limit, that is beta is close to 0, it produced results very close to what is observed in reality in terms of ratios of masses, and people thought this is good thing for lattice, but I was never happy. I was among a few critics of that, because the critical point of lattice gauge theory is that beta equal to infinity, which is as far as possible from the strong coupling limit, and this was just some accident. Now, fortunately, now no self-respecting lattice gauge theorist, tries to justify the success of the program based on strong coupling expansions. But this is something to keep in mind. For example, in the abelian Higgs model in 3 dimensions, the string tension and the mass gap, they scale differently. Their correlation functions are not proportional to each other. So you can define two continuum limits. One, you keep the string tension fixed so that you have a theory with finite tension, and the mass gap goes to infinity in such models, or 0. Or you can keep the mass gap fixed, in which case the string tension disappears and you have tensionless strings. So it is possible to define distinct continuum limits for the same lattice gauge theory. That's the end of it. Thank you for your patience. And with this, I have finished with one part of my lectures. Originally, this is all I wanted to cover, but now that there is some time and the organizers have been very kind to give me more time, I will tomorrow take up fermions on the lattice. Again, this is a vast area, I can't cover everything. I will try to highlight, some very, very important conceptual and technical aspects of fermions on the lattice. Thank you.
So this last observation, is it specific for this model, for this abelian Higgs model in 3 dimensions, or don't?
I'm a little hard of hearing,
Okay.
so
Does it?
somebody will help me. Yeah.
Okay. So the last point, is that only in this theory, or does it also happen in other theories?
Yeah.
So he is asking that two continuum limits that you have.
Yeah.
Do you have other examples?
I don't know whether there are any other example. It will be interesting to find them. That's why I suggest this, D equal to 1 model to look at exactly solvable quantum mechanics problems, and there you may be able to cook up something where not all correlation functions are proportional to each other. It will be very interesting, and in fact, it's a very important part of continuum limit of lattice gauge. Yeah.
I have a related question. These two different continuum limits, they do have different symmetries.
There are two different theories. In the continuum, they represent two different theories.
Symmetries are different.
Symmetries, I don't know, because in this model, the symmetry is rather simple-minded. So I don't know whether what kind of symmetries survive. It's an abelian Higgs model.
There's a string here. There's a string here, right?
String, yeah.
But I don't know about the mass gap.
Other one is, yeah, right.
Doesn't have. So
Yeah.
the symmetries will be different.